This is basically today's lecture on prediction of new observation or observations given an X, how you're going to predict the new observation and building up confidence intervals, so on and so forth. So this is the scope of today's lecture. Right. So estimate the mean response. This is our first target, to estimate the mean response. That is mean of Y, response variable. Suppose capital X, simple H, denote the level of X, right? We know we have several levels of X in our horizontal axis. When X is equal to 1, X is equal to 2, likewise. It doesn't have to start from 1 all the time. Wherever in your data set, you have a couple of observations for X's and Y's. So basically, XH denote the level of X, X1, X2, X3, likewise. That we want to estimate the mean response. So that is basically Xi, right? So XH denote the level of X, or the particular Xi, we are going to estimate the mean response. This is not the response, but the mean response. The corresponding mean response when X is equal to XH is expected value of YH and denoted by this. This is the notation that I'm going to use throughout the lecture. Basically, expected value means the mean, average. When X is equal to, or Xi is equal to this, the level of X, we are going to estimate the expected value of the response, or the mean value of the response. The point estimator of expected value of YH is this. This is how you basically denote an estimator by using the hat notation. In your second year course, you have learned in Mathematical Statistics 2 course, you have learned theta is the parameter, theta hat is the estimated value, right? So it is given by a function of observable random variables. So same idea here, the point estimator means what? We are giving an estimate, a point, a value for this particular quantity, which is denoted by this. And it is equal to this one. When we give the X level and we plug in the estimated beta naught and beta 1 values in our regression line, we are getting this. This is how we estimate a new observation. And this is not really the response. Remember, this is the mean response, which is very important. In interpretations, you have to mention the mean response, right? This is the mean response given the beta naught, beta 1, and the expected level of X. Right. This is also a combination of all the YIs, the new value, estimated value. For normal error regression model, which we discussed in the previous lecture, and with the result of linear function of normal random variables, this RV stands for random variables, we have this sampling distribution. So this is a random variable, this has some distribution, right? The sampling distribution of this YH hat, or the expected value of the new observation, or the mean response, sampling distribution of mean response, is normal with this mean and this variance. Whenever we are talking about a normal distribution, we always have to determine the mean and the variance. So here the expected value of this is basically this. We were talking about unbiased estimators. That is how when we take the expectation both the sides, these, since these are unbiased, they are going to be beta naught and beta 1 besides the hat. Expected value of beta naught is equal to beta naught. Expected value of beta naught hat is equal to beta naught. Expected value of beta 1 hat is equal to beta 1 because they are unbiased estimators. Okay, before by hearting these things, just try to play around what you have, right? How you got this. Okay, so this is the basic notation that we are going to use. So I think I introduced these notations in previous lectures. So sigma squared of this is not multiplication, this is just a notation. This means the variance of yh hat. Okay, this means the expected value of yh hat. Just like that, this is the variance of yh hat. It is going to be given by this formula, right? So this is normally distributed with mean beta naught plus beta 1 xh and variance, this quantity, you have to know this. The estimated variance of yh hat, why are we giving this? Because we don't know, this is a parameter. Sigma squared is a parameter, population value, population parameter. So we have to estimate this. Estimation of this, that means sigma squared curly bracket yh hat, the entire thing hat. We are not going to incorporate too many hats in one. So we used this notation. You should be familiar with this notation by now because we used this before. So what does this mean? This quantity hat means this, right? But we usually don't write that. So many hats, it's confusing. So we use another notation for this, right? So this is not population variance and this is not sample variance. You don't think things like that, right? This is the estimated variance of this. So variance of yh hat is basically this quantity, right? Clearly get these things into head. Estimated variance means what? This quantity hat, which is denoted by s squared, this quantity, right? It is equal to, same thing repeated here because all these are observable, and sigma squared is replaced by the mean squared error. We have discussed this before. Just because we don't know this. Right. So you have to know this as well. The variance of, did I skip a slide? No. The variance of yh hat is affected by how far xh is from x bar. What does this mean? Assume you have observations from x1 up to some xk value, right? So this is x1, x2, x3, x4, likewise up to k. Just for the moment, consider just two observations. You have two observations in your data set for the moment, right? x1 and x2. How did we get this particular regression line? By using just a sample out of our population. We have a population, we draw a single sample. We call it sample 1, just two observations. Particular x1 value with y1 value, x2 value with y2 value, and we construct the regression line, right? And this is the estimated y1 value that is given by y1 hat for this particular line. I'm talking about this point. And for this line, this is y2 hat. But it doesn't have to be the same all the time. These y values really depend on the sample. Assume that you got x1 and x2 and the corresponding responses from a particular sample. You call it sample 1. From the same population, you draw another sample. Just forget about the first sample with replacement or without replacement, doesn't matter. You draw another sample, which is called sample 2, and you plot these 2 points. It doesn't have to coincide with this because sample is sample, like it's coming out of the population. the regression line that you construct solely depends on your sample. It has to, right? So assume for x1, this is the y1 hat in your second sample. So you're getting a different regression line. When we take, if we take a third sample, it shouldn't have to be the same line, one of these lines. It can go along this. But the important feature here is, as long as you're getting the same x's, your x bar is constant. X bar means the mean of x's. You are drawing samples for the same x values and you're observing different y values. It's possible. If this is, let's say, this is the age of a person, this is the weight of a person. So in similar ages, in age, let's say we are taking from 1 to 10, 1, 2, 3, 4, up to 10, right? So it makes sense, right? When you take a sample, let's say you're taking samples from a classroom, you take sample of 2 people, two students. Okay, in a classroom, there are no aged 1 people. It's okay. From a hospital, you're taking age 1 to 10 from a clinic, okay? And you are getting the weight of them, right? So age 1 year child is weighed, right? And maybe this is that person's observation, right? When you weigh another child of age 1, he or she doesn't have to be the same weight as the previous one. So if we take one age, there could be different weights in kilograms or grams or whatever it is, right? So that is what this means. Depending on the sample, observation changes. It might change, it might not change. There could be same age people with same weight, but it doesn't have to be all the time. You all know that in practice. So that is why I said these observations depend on the sample, but as long as you're considering the same set of ages, same set of x's, you have the same constant x bar mean. If you are taking age from 1 to 10, your x bar is 5. It doesn't depend on the sample, right? You always read values for these ages. So this is constant. What does it mean? Whichever the sample that you take in a given range of x, it should go from this point. All these lines should go from this point. So the variance of our new observation, if we take it in the level of x, if we consider the level of x at a time, this particular level has a variance, because in normal error regression, this has to be normally distributed. This has to be normally distributed in normal error regression, right? That is what we are using throughout the course. So for a particular given x, there could be several y's, several responses, which means it has a variance, it has a spread. Variance means it has a variability. It is different. It is not the same. It is not coinciding in the same point, right? So the variance of YH hat is affected by how far XH is from X bar. So makes sense, right? If it goes along this point all the time, so we are getting lines like this, whatever the sample that we have, okay? So the variability really changes. Let's say this is the maximum Y1 hat that we got from the sample. Let's say we drew two samples, right? So we have 2 lines. If we have 2 samples, this is the maximum, this is the highest point, this is the lowest point. So you see a variability. When you keep on going far away, when this particular point keeps on going far away from the constant X bar, the variability increases. Makes sense, right? The gap between these two is less than gap between these two, and this is far away from x bar. When it gets closer to x bar, the variance is very small. So that is what they say. The variance of, because we are getting the sample from same levels of x. That is the reason. The variance of y h hat is affected by how far x h is from x bar. When we are going further away from the mean, the variability increases. Variability of y h hats increases. That means basically the new observations. Okay, sampling distribution of y h hat where sigma squared is unknown. So just because this particular thing is normally distributed, we know we can standardize that, right? How do we standardize? We subtract the expected value from this and divide it by the standard deviation. That means the square root of this. And it is going to be standard normally distributed. If this is normal distributed with this mean and this variance, if we standardize this by subtracting the mean and dividing it by the standard deviation, it is going to be distributed as standard normal. That is normal 0, 1. Mean is 0, variance is 1. But just because we don't know sigma squared and we are substituting, we are plugging in MSE on behalf of sigma squared as an estimation, it is no longer distributed as standard normal. It is going to be distributed as T. So sampling distribution of the standardized random variable y h hat, this is a standardizing, right? Where sigma squared is unknown, should distribute as T with n-2 degrees of freedom. If this is known, it has to be standard normal. By theory, you know that. Just because this is unknown, it's a parameter, it's unknown, so it is distributing as T. Whenever you are given this, it should follow a standard normal distribution, this quantity, right? So practically, we don't know this. So if we know the sampling distribution of a particular quantity, we are capable of constructing a confidence interval, right? So based on previous results, 1 minus alpha 100% confidence interval for this expected value of YH, right? So this is same, right? This one is equal to this one. Just notation. Here we discuss. Right? They are the same. Clearly get these things. So it is, just because this is T distributed, we are going to have the estimated response value here, plus or minus. T is symmetric around 0, so you can put plus or minus without any hesitation, right? For the upper limit and the lower limit. And just because it has two tails, it is going to be alpha over 2. If this is 1 minus alpha 100% confidence interval, the significance level is alpha. And the level that you have to consider, as it has two tails, it should be alpha over 2, right? And minus 2 degrees of freedom, it is coming here, times the standard error. So this one. That means the square root of this. Remember the square root. When we are going with so many notations, we tend to forget these things. This is the variance. They are talking about variance here, S squared. The square terms disappears when it comes to confidence interval. The square is not there. So when you are plugging in, don't plug in the squared term here. Always take the square root of S squared. So stick to these notation. This is the confidence interval for expected value of YH, or the estimated value of YH or YH hat. Right. So let's do a small exercise. Revisit the air freight breakage example, right? Find a 95% confidence interval for mean number of ampules broken when the cartoon was transferred 2 times from one aircraft to another over the shipment route. This is the question, right? So you should have, I will give you, you don't have to compute it once again. So for this, I'll give you necessary information that because you computed this in the previous lecture. So I'll give you information. You have to plug into the formula, construct the confidence interval, the requested confidence interval, and interpret it. Okay, I'll give you the data required. So just get this question to the head. They're asking for a 95% confidence interval for mean number of ampules. So ampules broken. Ampules broken is the response. So mean number of response. Mean response. They are asking a confidence interval for mean response, right? Where the cartoon was transferred 2 times from one aircraft to another over the shipment route. So this is the X, this is the Y. You're asking a confidence interval for YH hat. So let me give you the information. This is the model that we had. You don't have to compute it once again. It's a waste of time. You already computed all these. And I'll give you values. Sample size was 10. The sample size. I'll give you the value of MSE. You will need this. That is basically 2.2. What else do you need? SXX is needed. That is 10. We computed this. And X bar is needed, which is 1. Rest part you have to compute. I'll give the value of, no, you can get that from the table. So just write down this information. I think this is enough for the computation. Get these down. So you have to construct 95% confidence interval for YH hat. This is the question. I'll give you time. Do this and interpret. So this is 1. Second one is interpret. I'll give you time. Slowly take time and do this. Just because anyone didn't give me a response, I think the issue is that where you cannot understand the question. So if I recall, air freight breakage example had 2 variables, right? The response variable or the Y variable is the number of ampules broken when cartoon was transferred from one aircraft to the to another over the shipment route, right? So that number is going to be so the number is the response, right? How many times the ampule is transferred is going to be your predictor variable. X is, so it's like from one flight to another flight, they are transferring, right? For example, if you don't understand this, let's say some medicine should come from America to Sri Lanka, but there's no direct flight, right? They go from America to Qatar, Qatar to India, India to Sri Lanka. Just think like that. So how many times do they have to transfer from one flight to another, from America to Qatar, one flight? So when it's like staying in a transit, right? When you go abroad, you stay in a transit. It's something like that. So from you have to take the ampule bottle of the medicine has to get into another flight to go to India now, right? From Qatar to India, it has to go to the India-Qatar flight. So it is transferred from one flight to another. That is one time, right? Then India to Sri Lanka. So the target was from America to Sri Lanka. It is going all over the world and coming to Sri Lanka, right? It can be a direct flight. It might not be a direct flight. So if it's not a direct flight, there, of course, you have two times of transformation, right? Transferring from at Qatar, you are transferring from the American flight to the Qatari flight. In India, you are transferring from Qatar, you are transferring from Qatari flight to India flight, right? So likewise, transferring means you are taking the bottle out. It's like transferring baggage. If you have to go in two flights to go to some destination, your baggage is transferred from one flight to another. Sometimes you have to collect your baggage and transfer it yourself. Most of the time, they do it for you. Only the thing is, you have to get a step into the next flight. Your baggage is transferred. So it's something like this. It is basically that is the process here. Okay. So number of times that the ampule is transferred over the shipment route. Shipment means it doesn't have to be a ship. Basically, shipment means it can be a flight, it can be a ship, anything, right? So number of times. So this is your X. Did you recognize that? How many times the ampule is transferred, right? So this is your X. If you know X, right, you should be able to compute this one. You know X, this is 2. Now, did you understand how this became 2? If this is 2, you just have to plug in the values and compute this one. So just because this is a new observation, we came up with a new notation, but it's the same regression line that you have. So YH hat is, it's this I can go from 1 to n. So H is another sort of an n, right? So the first thing you have to compute is this one. Do you have any questions in computing this one? Any further? If you don't have a question, confirm me. If you have a question, please ask. Because you have to thoroughly get this into head. This is not hard. It's just the matter of understanding the question, and at the exam you have to remember the formula, but here I gave you the formula. Now give me your comments. Do I have to explain it once again, or did you get it? At least in the chat room, please let me know. Because I'm talking to understood. Okay, great. So I think this was the last point. So I'll give you 2 more minutes to plug in this quickly to the formula. This is the thinking point. You don't have to think anything, right? This is the first point that you have to come up with. Whenever you got this, there's nothing else to do in this, right? It's just plugging the values and computing. The calculator has to perform the task, not you. Okay, I'll give you a couple of minutes just because we have time. Today is a short lecture. So I want you all to come up with answers. Now do it. Okay, now I'm getting answers. Very good. ACE 2018-308 has answered correctly. 481 has answered correctly. 504, you have interchanged the limits. Your limits are correct, but you have put the upper limit to the front. So be careful. I know those things happens because when you compute these things in the calculator, I know you compute YH hat plus that quantity first, and then YH hat minus that quantity next, and then you're going to screw it up, right? It's okay to compute it in any order, it's okay, but when you're writing the interval, be careful. I'm emphasizing this because this had happened to me like million times. It has happened to me. When I see your answers, I know the reason behind that. So I'm not emphasizing your index number in everyone in front of everyone. It's not like this because everyone tend to do this mistake. I just want to emphasize the fact that these can happen. Okay, so make sure you write the lower limit in the left hand side and the upper limit in the right hand side, because at the exam it's in vain, like you're losing marks. Okay, so very good. 3, 4, 1, 4, 2, 6, all of them have have reached the answers. I'm happy. So I think you should be struggling with this one. So you could have asked me in the chat room how to get XH, how to get YH hat. You could have asked me, then I should know. I have to do magic here and guess your difficulty. Anyway, fine. So I'm happy with your answers. So I'll do it on board so that the ones who still find it difficult can get some help from this. And those who reached this one, try to interpret and send me the interpretation. I have taught you how to interpret a confidence interval when we were constructing confidence intervals for beta naught and beta 1, right? For regression parameters. Same way you have to interpret it. Let's see whether you can do that. Try this. Till you try that, I'll do the working for the rest. So the formula is, those who reach the answers don't have to look at the board. They can just try the interpretation. Others look at the board. 95% confidence interval for YH hat, or you can say expected value of YH, doesn't matter. So you even can say when XH is equal to 2. Doesn't matter, you can either have this or not. So this is equal to 18.2. This is 8 plus this quantity is 18.2 plus or minus, right? Then what is the value here? This is, I'll just write the notation first. T n minus 2 alpha over 2. Here you have S so this is basically a confidence interval. So here actually I'll do the notation for those who find it difficult. So n is 10. 10 minus 2 will give you 8. Just because this is 95%, what is your alpha? Alpha is 0.05. So if this is confidence level is 95%, significance level is what? 100 minus confidence level. That is 5%. 5% when you write it in decimal, it's 0.05. And you have to take alpha over 2. So that means 0.05 divided by 2 times this one. So you have, I'll write it there. MSE 1 over n XH. So you have to know these. I'm not giving you formulas for these. You have to know. And you have to take the square root, remember that. So you had taken that, right? So this is basically 18.2 plus or minus. This one you have to read from the table. This is T8, 0.025. This is 2.03. We read this one last time, so I'm not going to reread it. So 0 times square root of MSE, it is 2.2, 1 over 10 plus our XH is what? There were 2 transfers. So this is 2. In the question it says minus X bar I gave you, that is 1 squared over SXX I gave you, it is 10. So these are the plugins. So you have 16.6704. You can keep up even 2 decimal places, doesn't matter, but keep it correctly. Don't write 16.68, then it's wrong. This is 0, this should be 7. 19.7296. This is the answer for this one. Chat room, I am getting okay, I'm getting nice answers in the chat room for the interpretation. I can be partially happy with. This is what, when you're interpreting something, make sure you use plain language. I know we did beta interpretation by using the word beta because we didn't have any other name for that, right? But here, what do you mean by YH? There is a English word or English phrase for that. Technically, all the interpretations that came to the chat room are correct. Technically, I got 2 interpretations from 308 and 343. Technically, they are correct, but you can't say YH. Right? In interpretation, you have to give what YH is. And basically, it's not YH. In the beginning, I told you it is the mean. So it's YH hat. So somebody has interpreted as YH hat, technically correct. But interpretations can't be technical. Okay. So I'll write the interpretation for all of you. Good try, very good attempt, right? You have not misinterpreted this. The thing is, there were a little bit slips here and there. So write down this interpretation. So I'll clear this off. You all can take a screenshot, those who couldn't come up with the answers, but please try these ones again. So the interpretation is basically, everyone write this down. We are 95% confident that. So one answer was YH hat lies between 16.7 and 19.7. That is okay, but you have to say what YH hat is, right? So the best interpretation that you can give here is, what is our response? And we are getting YH hat, not YH. So that is basically the mean number. Y means what? What is our response? Number of ampules broken when they are transferred from one flight to another flight, right? So what we are having here is the confidence interval for YH hat, not YH. So what do you mean by YH hat? It is the mean number of ampules broken when transferring. It's not the number of ampules broken when it is transferred. number of ampules and mean number of ampules are two different things. Okay, so here what we computed was the mean number of ampules broken when the transferring happens. Okay, so you can say we are 95% confident that the mean, if this word is not there, interpretation is completely wrong. Okay, the mean, so you can construct the rest according to the problem context. So here, mean number of ampules, you don't have to underline, I just emphasize the word, mean number of ampules broken. So you can copy this down from the question itself. From here onward, you can copy it from the question. That's the easiest way. When the cartoon was transferred it's better to give some idea about the X as well, because expected value of a particular observation depends on the X level. So it's better to give the X level as well, idea about the X level as well. So easiest way is copying from here to the end until you write the confidence limits, right? Copy it from the question, because the question is clearly specified what you need to compute. That's the easiest way. We are, whatever the percentage it is, confident that copy from the question and say lies between these two values. So when copying the question, carefully extract the words that you want. Was transferred 2 times from one aircraft, you can say. Should write it properly. To another. So have this also, because if it is 3 times, the mean number of ampules broken is going to lie between a different confidence interval. So have this one as well. Mention about the X level as well. Okay. To another, lies between the computed, you can just say like this and this. So just because this is number of ampules, you can either say lies approximately between 17 and 20. You can say that even. It's okay. Because they're talking about a number. Mean, just because it is mean number, even it is okay to have it like this. Because when we average things out, it can accommodate decimals. So it is not wrong to say like this. It's not incorrect to say like this, just because it's a mean number. But if you want to make this more sensible, like if you want to forget about this and just because we are talking about a number, you can either keep it in integers, but don't say it's between 16 and 19. It's wrong. When we round it off, properly round it off, you can say between 17 and 20. Or you can have this, nobody can put wrong, because this is the confidence interval that you got. Okay. So theory and practical things have some gap. So theoretically, this is how you interpret a confidence interval. But when you apply this in practice, you know this is between 17 to 20. It is okay to know that and write it like this way. Totally fine. It's accepted. And make sure you give this one as well. Idea about the X level. Okay, don't forget this. So those are the things that you have to be careful about, and don't say there's 95% probability. Don't use the word probability, it's wrong, right? It can either lie between these two or not. If it is lying between these two, the probability of happening this event is 1. If it's not lying between these two, the probability of happening this event is 0. So we are not talking about probabilities, we are talking about the confidence. So we are 95% confident that the mean number of ampoules broken when the cartoon was transferred 2 times from one aircraft to another lies between these two values. I think that is clear to you all. You can copy this down. Make sure you give the idea about X. That is the best way, because whenever this is changed, you can know, right? These things have to change, because we got the confidence intervals by making use of YH hat plus or minus. How do you compute this? Beta naught hat plus beta 1 hat XH. So you have to give the idea whenever this changes, this one changes accordingly. If this changes, the confidence interval changes. That is why it's important giving some idea about X level as well to make the answer complete. So remember that. Okay, good try. Next one, prediction of new observation. New observation on Y to be predicted as a result of new trial. When you do something new, you are not taking things out of the sample now. By making use of the sample, you constructed the regression line. Now you're getting a new observation, right? New trial, you're doing a new trial. You're not dealing with the sample any longer, but it is advisable to keep the range of new trial between the range of X. No, I should say it's advisable to keep the value of X between the range of our regression. Otherwise, we do not advise extrapolation. We don't know how the regression line fluctuates or changes besides the given range of X. We discussed that thing before, right? Anyway, it's a new trial. The new response is denoted by this one, just a notation, like this is a new one, right? At the new trial, this is just a notation, so don't try to confuse yourself. What is YH? What is this YH new? Just these things are just notation. Same thing. Okay. In the previous section, we estimate the mean of the distribution of Y at a given X level. That is why in the interpretation also I emphasize the fact that you have to mention the word mean. We were talking about the mean. In the regression line, we were talking about the mean, not about a single observation. Now we predict an individual outcome drawn from the distribution at a given level of X. So this is just one way. All these are done for the mean, YH hat, expected value of YH hat. We did things for this one, the mean, right? Now we are considering the individual outcomes. It depends on the sample. We discussed that, right? Earlier case, we considered the mean of these two, if there are two. Now we are considering these individual things. Okay. So the confidence interval is going to be wider than that. In that case, you will understand that. So just keep that in head. Because you have to accommodate all the observations individually. We assume that the underlying regression model is applicable for new observation as well. So wherever it is, how do you predict this, it's the same way. You have to make use of the regression line that you constructed. Earlier case, we considered the mean of y at a given x level. Now we are considering the individual outcome at a given x level. Two different things, mean and individual outcome, they're different, right? So now we cannot be certain the location of the distribution of y. Yes, because there are so many y's in a particular x level. What does it mean? If we draw a line, so we constructed the confidence interval for this at a given x level. So if there are 100 x levels, we have 100 confidence intervals, right? So when this is 1, this is 2, this is 3, 4, 5, likewise. Number of transfers in our problem, right? So when the number of transfers were 2, we had a confidence interval for this. This is the mean. Y2 hat, when HC is equal to 2. This is the mean. Y3 hat. What we computed was this 16.7, 19.7. That is this interval, right? So depending on the level of x, the interval changes. That's why I said in the interpretation of this, please specify this one as well, because it's not in general. But this is what we discussed. Now we are going to discuss about all the observations, right? So there could be many observations. So we are considering all these. So it has some variability. Earlier case, we considered only this one. Now we are considering all these to construct a confidence interval. So that is why when we consider everything, when we take everything into account, in this one also has some variability. It captures everything, right? So the confidence interval is wider than this one because it captures all the new observations. These are the observations in the sample. This black one covers the observations in the sample. That is how we got the mean. Whenever we get a new observation, it doesn't have to fall within this confidence interval all the time. For this given x level, it could be wider, right? It could go even beyond this. Whenever we get a new observation out of the sample, now once we constructed the regression line, we are not referring to the sample any longer. We don't need to. Why we constructed a regression line using the sample is to use it in the future. Whenever we get a new observation, we plug in that to the regression model and we predict the result. So the new observations can go anywhere. It doesn't have to stick to this boundary. Now we are constructing confidence interval for any given new observation, not the mean, not the average. So it should be wider because it has to accommodate more space. That is the idea. That is why it becomes wider. So now we cannot be certain about the location of the distribution of y because we don't know from where it is coming. It can go in a wide range. We are not very certain about the location. If the mean, we are certain about the location because it depends on data. We know the mean, we know how to average out. But here we don't know. We are not certain. So we can have a confidence interval. So you call it prediction limits. So this is basically you call it a prediction interval. Of course, this is a confidence interval, but you give the name prediction interval for this. So these are the prediction limits, lower limit and the upper limit. Whenever you are asked to construct a prediction interval for a new observation, this is the formula. Whenever you are asked to construct a confidence interval for mean response, confidence interval for mean response, this is the formula, right? Prediction interval, or you can be given the word confidence interval, that's fine. For a new observation, this is the formula. Usually we use this word, prediction limits, prediction interval. So this is basically the prediction limits. These are confidence limits. These are confidence limits because we are confident about that. These are prediction limits. Still we are confident, but those limits are given a name called prediction limits. The lower bound and the upper bound are called prediction limits. Same thing, because we assumed that underlying regression model is applicable for the new observation. Just because of this, we are going to have YH hat here, right? Same t-value, because it's the same distribution, we assume that. This one changes. Why? Because it becomes wider. We have to accommodate all the new observations in our prediction limits. So the variance term, the standard error term, gets different. That is the only difference between the confidence limits and the prediction limits. Only this part changes. Everything remains the same. The variance of a prediction error depends on two components. Variance of the distribution of y at a given x, namely sigma squared. Okay, and the variance of sampling distribution of YH hat, namely sigma squared YH hat. So at a given x level, we have the sample data. We have to consider the distribution of that, and also the distribution, sampling distribution of the new observation, because it can go beyond the limits, right? So we have to consider two different things. The variance of a prediction error, you call this the prediction error. This is the actual one. This is the error, plus or minus error. This particular prediction error, we take it with this term. Only this term changes, but error is this one, plus or minus error, right? So we have to take into account both these. That is why it becomes wider. When we have to accommodate more things here, these boundaries get wider, plus and minus wider, right? It's very visible. So what is the S squared of predicted value? It's the MSE. So that is for this and this one. Sampling variance of sampling distribution of YH hat. So you have to do the same thing. You have to add this additional MSE term for the previous one to get this one. And remember, in the confidence interval, you have to get the square root of this. Please remember that all the time. This is S squared spread. This is S spread. Right. So this is when this particular thing is plugged in here, and whole thing, so they have plugged in value for this one, the formula for this one, and they have bracketed that, taken the common MSC term out, because this one also has MSC. What is this one? MSC times this quantity. So they have taken the MSC term out, 1 plus this quantity. So basically this is the formula to compute this form. Confidence band for regression line. Confidence band for regression line helps us to see the region in which the entire regression line lies. So when you keep on constructing confidence intervals, right, you can create a band. Let's say you have a line like this. Okay. And let's say these are your X values, X levels that you have incorporated in the sample, very simple example. Okay, so you have these observations. Whatever between these observations, you can use the equation of this line to predict. For all these, we can construct confidence intervals, right? Same gap here. Just make sure you have the same gap. So basically, the confidence band is this one. You join all these upper limits and lower limits. So this is your confidence band for the entire regression line. You can have the prediction limits, which are wider than this. Okay, and this is the confidence band for the prediction limits. Sometimes it is called the prediction band, but sometimes you can say it is the confidence band. So this is the confidence band for confidence limits, right? This is the confidence band for prediction limits. So some people say prediction band. They don't say prediction band for this. Just because this is drawn for prediction limits, they call it prediction band. But it doesn't matter. You have to know how to construct the limits and what do you mean by the band. It's just a matter of joining all these. So you can say prediction limits are wider than confidence limits. You don't have to draw this because it's there in the last slide. Just get some idea. So confidence band for regression line helps us to see the region in which the entire regression line lies. So confidence limits or the prediction limits, they are given to get some idea about the particular X level. When it comes to a band, it gives an idea about the entire regression line, not only the X level, because there are gaps between X levels, right? So if we consider only this one, It is given for this X level. But what about from here to here? We don't have we can't construct infinitely many confidence intervals. We can, but in practice, we don't do that. What we do is we construct confidence limits or prediction limits for every X level and we join them. There we get the band. So we think this is the limit of this particular level. This is X1, this is X2. So in between, for this level, we say this is the confidence limit. So we construct that by using the band. That is how we do. So that is why it says, just because this is a continuous line, that's why it says it gives idea about the entire regression line rather than just the X level. That is the meaning of that sentence. So 1 minus alpha 100% confidence band for the regression line at any X level is given by this formula. So this is not sums of squares of this is not that thing. W squared is basically this one. This is just like the critical value. It's something like this, F distributed. So 2 times F, this is the numerator degrees of freedom. This is the denominator degrees of freedom. And when you are plugging in the value here, you have to take the square root. W squared becomes W. This one, this is the one. So this is basically the confidence band. Okay. If it is the prediction band, you have to have 1 plus 1 over n plus this. Okay. So we'll go with those things. This is the confidence band, right? If it is the prediction band or the band which is drawn for the prediction limits, the wider band, you have to have 1 plus here. So this formula is given for the black band. This one. For this one, this black band, confidence band. We'll just take off this word from here. Otherwise it's confusing. You might be wondering whether the formula is given for this one or this one. So I'll just remove this word from here. Prediction band for prediction limits. So in case if you want to get the prediction band for prediction limits, you just have to change that term. Add 1 plus. So the formula is given for confidence band, which is drawn for confidence limit. How did I identify that? By this term. This is the term. This is how you construct the band. No, this confidence band is able to draw conclusions about any and all mean responses for the entire regression line and not just about the mean response at given X level. So when you compute this, you're getting at each X level, right? Because you're substituting X's here. So you have to make note, the band is not for only the X level, it is for the entire regression line. Okay. And not just about the mean response at the given X level, hence the band is a bit wider than the confidence limit for the mean response at XX. So it says it's not touching these lines, right? It's a bit wider than this, going like this, a little bit wider, it doesn't have to touch. Okay, So here is the graphical representation. So red solid line gives you the regression line, and green line gives you 95% confidence interval. So basically the confidence band, and this line gives you 95% prediction interval, basically the prediction band. You don't have to copy that down. So this is for the ampule cartoon example. So number of broken ampules are coming with the y-axis, number of transfers comes to the x-axis. So this is the regression model. This is the model. So they have constructed the line. So what I want to show you here is this confidence band is less wider. It's smaller. It's narrower than the prediction band. That's what I want to show you. So I think that is it for today. Yeah, it's finished. So from today's lecture, if I give you a small recap, you have to know this. Just try to distinguish between the mean mean response and the actual response. So for mean response, this is the confidence interval. For actual response, the prediction limits is going to be wider. So you have to know this one and the previous one. So always this is for a new observation. When you are interpreting this, you don't have to use that word mean. We are 95% confident that mean number of ampules, you don't have to say that, right? You can say predicted number of ampules, something like that, or you can just say number of ampules. You don't have to use the word mean. So just know this prediction of a new observation, and these things. This formula is, I don't say not to study, but you know, this is worthless doing because this is constructed for a particular X level. So when you are constructing the band, you have to construct these things and then join. That is the idea. So yeah, that is it for today. Thank you very much for participating in today's lecture. You all can leave the meeting if you don't have any questions. Thank you very much and stay safe.